Hi, welcome. This is the mock exam number 1, and we will proceed to answer all the questions. Okay, question number 1 is without the structure, provide the UPAC names of the molecules provided below. It's necessary without wedge and dash bonds to show stereochemistry. Okay, the first one, what we have is a Z 3-bromo 4-ethyl 2-methyl ethanol. That means from here we can check that this we have an aldehyde. Now this means that we have a double bond in the third position, and this is the main chain. That means F, I will draw the main chain. 1, 2, 3, 4, 5, 6, 7. Okay. And then I put the functional group that is the aldehyde. Okay, in position 3, 1, 2, 3, I put the double bond. Okay. Then in position 2 I have a methyl. In position 4, 1, 2, 3, 4, I have a methyl. And in position 3 I have a bromo. Okay. Then again, if we calculate here, then I have to check which is the configuration of the double bond, that is Z. Here the double bond will be Z because in this side, the bromine has the priority, in this side the propyl has the priority. That means that the final compound will be exactly what you saw in the slide. Second is N-ethyl, N-methyl butanamide. Okay, we will analyze point by point. Here means that it's an amide, and the main chain will be butan, that means 4 carbons. I will draw 4 carbons. 1, 2, 3, 4. And then I put the amide here. Okay, and then they say that they have two substituents, N-ethyl and N-methyl. That means that the methyl and methyl are bonded directly to the nitrogen of the amide. That means put it, and this will be the final compound. Okay, in this case, we have this compound. This is an aldehyde, okay, bonded directly to a ring. That means that will be, in order to do it, we have to name the ring and then put carbaldehyde. Okay, if we name the ring, this will be a 4-hydroxy, Y4. Remember that because the aldehyde is the main group, the main functional group, we will start counting from here. That means that the hydroxy group is the number 4. That means, and the cycle is a cyclohexane. That means that if we put all together, this will be cyclohexane, carbaldehyde, okay, and at the beginning we have to put the 4-hydroxy 4 hydroxy hydroxy cyclohexane carbaldehyde. Okay? And the last thing that we need to do is to put the stereochemistry. In this case, the OH is going up, the aldehyde is going down. That means that will be trans. Trans 4-hydroxycyclohexane carbaldehyde. Okay? If someone is asking me if we have to put the stereochemical descriptors, that means if each center is R or S, this molecule is not chiral. It's a mesocompound because we have a plane of symmetry. Okay, you can see here. Okay. Next one. First thing that I have to do is to identify the main group. The main group is here. This is a acyl bromide. Okay. And then the main chain will be this. 1, 2, 3, 4, 5. That means that this will be a penta. Remember, when we have 5 is pentan, and then because it's an acid bromide, sorry, will be oil. Is the termination for acid bromide, acid chloride, acid diurite, pentanoyl, sorry, pentanoyl bromide. And then the only that we need to put is the substituents. Remember, because this here is the acid bromide, this will be carbon number 1, 2, 3, 4. In the fourth position, we have two substituents that will be a methyl and a phenyl. Which will be named first? The methyl, because it's for alphabetical order. That means that what we will have is a 4 methyl, 4 phenyl pentanoyl bromide. Okay? Good. Next one. Here, the first thing that we need to identify is that this is a ester. Okay, that means how is called the ester. Basically, we have this part that will have an ending that 8. Okay, and the other part that is after the oxygen of the ester, this determination is like a substituent. Next thing to do is to try to find the main chain, and the main chain will be exactly this. Okay, 1, 2, 3, 4 will be a butan. Butan. 8, okay, because it's an acid. And then we put the substituent that will be 2-methyl butanol. Okay? And then what we have to put is to put the substituent that is this. This is a isobutyl. That means that it will be isobutyl 2-methyl butanol. Okay? No, it's not iso. Sorry, I made a mistake. It's a sec-butyl. Sorry. Sec-butyl 2-methylbutanoate. Okay. Next one, we have this compound. Okay, and the important thing is to remember that all this compound is called phenol. Okay, that means that this will be a free isopropyl phenol. Why free? Remember that if the phenol is the main group, this will be carbon 1, 2, 3. Okay? Or also we can say that it's a meta-isopropyl phenol. Meta instead of free, we can put meta. Up to you. Okay, remember ortho meta para. Ortho is when we have two substituents in a benzene ring 1, 2. Ortho is 1, 2. Meta is 1, 3. And para is 1, 4. Okay? Good. Then question number 2, add the curved arrows to show the full mechanism of the following transformation. Okay, reaction 1, basically this is an acid base. Okay, and remember always what we saw is the movement of the electrons. That the pair of electrons of the bromide will take proton, and then this pair of electrons are going to the oxygen to get the final compound. Next one, the pair of electrons of the oxygen attack the electrophile, okay, and then at the same time, because we suppose that it's a SN2 reaction, the chloride is departing, that is the electrons forming the carbon chloride bond are going to the chloride to generate the final compound. In this case, what we have is the addition of a nucleophile. This is a nucleophile. And what is happening is that the pair of electrons is attacking the carboxyl group, and in order to avoid the octet, this pair of electrons are going to the oxygen to generate the final compound. And finally, the last one, what is happening is that the pair of electrons of this oxygen are recovering or reforming the carbon-oxygen double bond, and the carbon-oxygen bond, in order to don't break the octet, is moving to the oxygen to form these two compounds. Okay? Question 3. Draw the structures of the product for the following reaction. Okay? If we do the following reaction, what we have is that we will get this compound. Okay, and then remember that it is the addition acid derivative that will start with the nucleophile addition at the carboxyl position, and then we form the tetrahedral intermediate. Next, we regenerate the carbon-oxygen double bond, and the leaving group, in this case the chloride, is leaving to generate this final compound. And remember that we don't like to have anything positive or negative, we want to have neutral compounds. If we have a positive, the only that we need to do is to remove one of the protons of the mite, and what we generate is the final compound, that is this. Okay? Next one, what we have is this compound. Okay. Sorry. I will write it again. Okay, this double bond attacks the carbonyl compound, attacks the carbocation, sorry, and what we generate is this compound. Okay. Okay, and then this compound, the hydrogen, is eliminating, and what we get is the regeneration of the benzene. Okay? Good. Problem number 4. For the given molecules, which one is more acidic? Well, in the first one we have 2 alcohols, but in the alcohol B we have a very electronegative group. That means that will increase the acidity, will decrease the pK. Okay? Question 5. For the given molecule, which one is expected to have a higher boiling point? Basically, in the molecule B, we have van der Waals forces, we have dipolar forces, while and hydrogen bonding, while in the number A, we have van der Waals forces, dipolar forces, and hydrogen bonding. But we know that the carboxylic acid always will be more acidic than not an alcohol. For this reason, the hydrogen bonding will be bigger, will be more strong, will be stronger hydrogen bonding. If we have a stronger hydrogen bonding, this compound will have higher boiling point and higher melting point. Okay? Question 6. For the given molecules, which one is expected to be more acidic? Okay, again, we have in this case a phenol and an alcohol. And in this case, what we have to check is that when we have the phenol, we will put the acidic reaction, okay, the dissociation of the phenol. Conjugate base plus the proton, but this conjugate base can be stabilized by resonance. Okay, these 2 electrons here, this pair of electrons here, and then what I have this compound. Okay, this also can be. We have another resonance form. One more, move the electrons here, this is going here. That means I have 4 resonance forms. Okay, while if I do exactly the same for the alcohol, what I get is I get the conjugate base plus the proton, but this conjugate base cannot be or cannot have any resonance form. That means because the conjugate base of the phenol has 4 resonance forms, means that this is more stable, and if this part of the equation is more stable, will be more acidic. Okay? If we put the product more stable, means that the reaction will go through the products. Question 7. For the given carbonyl molecule, which is expected to be more reactive towards nucleophilic addition reaction? Remember that when we are doing this, okay, basically the reactivity of the carbonyl molecule is coming from, I put an example, okay, of aldehyde. Because the oxygen is more electronegative than the carbon, we have a density negative charge here and a density positive charge. The density positive charge of the carbon will determine how good a electrophile will be this compound. When more positive, more reactive, the nucleophile that is a friend of positive charge will attack faster and better. Okay, but what we can do is that when we are using A, okay, this is the resonance form that explains why the carbon has a density positive charge, because we can do this resonance form, but this resonance form can have other resonance forms. Electrons and I have this, and finally I can do this. Okay, like now I have 4 resonance forms for this one. If I do the same for the compound B, I don't have any extra resonance form. That means I am stabilizing this resonance form. That means I am stabilizing the starting material. The starting material is more stable, means less reactive. Okay, because I am stabilizing the starting materials, will have the reaction will go to the starting materials, not to the final products. Okay, question 8. For the given 3 molecules, order the reactivity from the most reactive to the less reactive in SN1 reaction. Okay? In SN1 reaction, what is the most important? The most important is the stabilization of the carbocation. Okay, which will stabilize better the carbocation? Well, if we check all the possible carbocations, that basically would be the positive charge here, here, or here. Okay, all are tertiary, but obviously these compounds will present a stabilization by resonance. Okay, that means that we can do, when we form this compound, we can stabilize this, and what we can generate is this compound. That means, in this case, in the case I and B, Because I can generate different resonance structures, that means that this carbocation will be more stable. That means that the reaction will go better. Remember that the key for SN1 is to stabilize the carbocation. Okay, then what more is different? Well, the different also is the leaving group. Which is better leaving group, the bromide or the iodide? Well, remember that the leaving group is how easy it is to break the carbon-halogen bond. Remember that iodide is bigger than not bromide. That means the overlapping between the carbon and the iodide will be worse. That means that this will be weaker. If the bond is weaker, okay, the carbon-iodine bond is weaker, means that will be easier to break. That means that A will be the better reaction to do SN1, the better substrate to do SN1. Okay? Go for the next one. Here we have 3 molecules, and the reactivity, we have to put the most reactive to the second most reactive in SN2 reaction on the center. Now we are in SN2. Remember that the most important is that the nucleophile will have an easy access to the carbon electrophile. That means when more substitution, worse will be. That means for only this reason, this compound will be the most reactive. Okay, then the other 2 compounds has a secondary carbon here. Okay, this was a primary. And as a leaving group, we have a bromine and we have ammonia. Which is better leaving group? Bromine, because it's a halogen. That means that this will be the second, and this will be the left. Okay? Okay, question 10. They say that hydrogenation of the 3 given alkanes produce the same product as in the given reaction. The energy diagrams of these reactions are provided by the same graph below. Level the curve for each of these 3 alkenes on the graph based on the stability of the alkenes. Okay? We have these 3 alkenes. Which will be more stable? We know that double bonds, when more substituted, are more stable. Why? Because we have the hyperconjugation of the orbital sp3 of the carbons that are directly attached to the double bond. That means this carbon, this carbon, and this carbon, and this carbon, this carbon, and this carbon will, the sp3 orbitals of all these carbons will stabilize the double bond. That means when more substituted in the double bond will be more stable. That means that this will be the more stable because this text substituted. This will be the second, the B will be the second more stable because it's still substituted, while A will be the least stable. Then the only that we need to do is to go to the graphic, and which will be the most stable? The most stable will be this compound. This is the more stable, that means molecule C. This will be the second more stable, will be B, and this is the less unstable, that will be. Okay? Question number 11. For a given substitution reaction, the reactant has R configuration. After the reaction, 2 products were obtained with opposite configuration. Is the reaction likely to be SN1 or SN2? Give a brief reason. The reaction must be SN1, sorry. Why? Because remember that it is SN2, and we have, for example, this compound, okay? And we substitute X by Y, what we get is that what we get is that we get a change of the configuration. We have an inversion of the configuration and we get only one product. Okay, this is chiral as they say. However, if we have a SN1, remember, I will put the same reaction by SN1. We start by the same chiral compound, okay? But now, remember that the first step is the departing of the leaving group. And what we generate is this planar carbocation. This planar carbocation, and then Y is coming and can attack from the upper position or from the down position, giving us two different products. Okay, that means that the reaction must be SN1. Okay. Okay, next question. If you are given the below substance as solvents, which solvent might be the best option for the reaction in A? That means, remember that the reaction in A is a SN1 reaction. That means we need a solvent that must be polar and protic, because it's the one that stabilizes better the carbocation. That means that the only polar protic is this. The other two are polars, but they are not protic. Polar, protic, stabilize better the carbocation. Okay. Good. Then we go for the next question. Question 12. Which, for the given of three molecules, which is organic, antiaromatic, and non-aromatic? Okay. We have to apply the Hooke's rules. Remember, the Hooke's rules are planar. All carbons, all atoms of the cycle must be sp2 or have a p system, and then is following the 4n plus 2 electrons to be aromatic. If we are following the 4n, is anti-aromatic. First one, all is planar, all the carbons are sp2, one because they have a double bond, the other because it's a carbocation, that means it has sp2. Okay, and how many electrons we have? 2, 4, 6 electrons. This will be aromatic. Okay. Question B is the compound B. All carbons are sp2, but in this case we have 2, 4 electrons, anti-aromatic. And the last one, what we have here is a carbon sp3, non-aromatic. Okay. Okay. Complete the following reactions by adding the missing products. Okay. Here, remember, is the attack of a nucleophile to a carbonyl group. This will attack here following the Burgundy-Dunit's trajectory. Okay, what we will get is this compound, and then we create with acid. The part of electrons of the oxygen will attack the acid, and what we will get is we will get this compound. Okay, now a nucleophilic acid substitution. What is happening? Remember, the nucleophile will attack the carbonyl group, and in order to don't break the octet, the carbon oxygen double bond has to go to the oxygen. What we will get this compound. Okay, next step, the pair of electrons of the oxygen are recovering the double bond, and the leaving group, in this case the chloride, is departing to form then simply we remove the proton, because remember, we don't want anything charged. We remove a proton of the amide, and what we get is the final amide. Okay? Next reaction, we have an addition reaction of a double bond plus bromine. Remember that the first step always will be the formation of the bromonium ion. Okay, I will draw the bromonium ion down. And then the bromide will open the bromonium ion opposite to the first bromine, to the bromine of the cycle. That means that we will get the Kranz debromination. Okay? Always we will get the Kranz debromination. Okay? One, we have a substitution reaction. Here we have this compound. Okay? It's a secondary electrophile. That means that we can suppose that can be SN1 or SN2. However, if we check the solvent is polar, no protic. That means this indicates that probably will be a SN2 reaction. SN2, this will attack from behind, and at the same time the group will depart to form this compound. And remember, because it's SN2, what we have is an inversion of the configuration. If the bromide was in our direction, now we will have the methoxide in the opposite direction. Okay, then we have an addition reaction. Basically, we have double bond, and we react with mercurium acetate. First step, remember, is the formation of the mercurium, the free member ring with the mercurium. Okay, and then the solvent, in this case water, is attacking the position more substituted, because it's the position that stabilizes better the density positive charge. That means that we will have is the addition of the solvent, in this case water. Okay. To the most substituted carbon, and what we get is the mercury in the other position, and then we add sodium borohydride that the only that it's doing is substituting the mercurium acid for a hydrogen. Okay, good. Next one, we have electrophilic aromatic substitution. What is happening is that the chloride reacts with the aluminium. This is a Lewis base, this is a Lewis acid, and what we form is, in a first instance, we form this compound, okay, and then benzene do electrophilic aromatic substitution, forming this compound. Okay, and we lost a proton, and we regenerate the aromaticity to obtain this final compound. Right? Good. Here we have the Williamson reaction. Okay, we have an electrophile, a nucleophile. Basically, the pair of electrons of the oxygen will attack the electrophile, and because it's a primary, the bromine, the pair of electrons that are forming the carbon bromine will be both the bromine, that means we are forming and destroying the bond at the same time. And what we get is this compound. Okay. Finally, we have question number 14. The energy profile of a three-step reaction is given below. Answer the following questions based on the following diagram. Okay. Which step is the rate determining step? The rate determining step is the one that has the energy activation higher. Energy activation of the first step will be from here to here, isn't it? That means that is B. The energy activation of the second step will be from here to here, means basically C. And the energy activation of the third reaction, the third, will be from here to here, basically F. Which is bigger? B. That means that will be the first reaction. Second question, which is the level of the Gibbs energy change of the second step? Endorgonic or exergonic? In the second step, we have from here, the starting material of the second step, until here. That means that is more stable the final product. The energy, the variation of Gibbs of the two step will be F. No, will be E. Sorry. That means that is exergonic, because the final products are by far more stable than the static materials. Okay, label the gradient state of certain step as TS3 in on the feature. Okay, the TS3 must be this. Okay, it's a maximum of energy and of the third step. Which is the level of the activation energy of third step? We already did it. Okay. Label the intermediate of the first step. There are no intermediate in the first step. There are 3 consecutive reactions. And finally is the overall reaction. Is the overall reaction product or reactant favorite? State your reasoning with a brief explanation. Okay. What we know, if we check the diagram, is that the final products that are here are more stable than not the first. So variation of heat of the total energy is equal to A. Okay, and A is negative. Okay, because the final products are lower energy than not the starting materials. That means that the reaction will be exogenic, the global reaction. If the final products are more stable than the starting material, the reaction will have tendency to go to the top. Okay, I get that there are no more questions. Let me check. No more questions. Thank you very much for your attention, and I hope that this helped you in order to study. And see you in the next mock exam.